8.6 is on integration by tables, and we have sort of done that already when we derived formulas for inverse trig functions. So this is the more general way of looking at it. In the first case here, I went ahead and gave you the formula directly. But we can see, so how you do this is you have this integral, and you want to say, okay, what's the antiderivative, and you look to see this form. So the form of this is a square on the outside in the denominator. Then you have a root, and it's critical that you see that it's a sum. And then now that 3 is just a constant, and then here's something squared. So the constants are causing us some problems here, because it's not like, normally you might want to see that as a 9 or like a 4x squared, but it isn't. So it's close to looking like this. And the question is, can you manipulate it so that it looks exactly like this? And you may have to have integration constants to make this work. So this, and then if you can get it to this form, then you can go directly to the formula. So what you do is you let certain values be your u, but then you still have to do the du chain rule stuff. So what we see then, we can let u squared equal to 5x squared, so that it's this whole thing is my u squared. But if you do that, your u, which is what you're substituting back in here, would have to have that root 5. And keep in mind everything's positive here. So so then that would mean my u is equal to the square root of 5x. And then my a squared would equal the 3. Actually, let me put that back over on the other side underneath this. So we see that a squared is equal to 3. So then you would have, and actually, your a squared, when you substitute, that's not going to change anything, because you're just going to put 3 back here. So you don't really have to do a in this case, because what you substitute back, this a squared, like assuming we can do this is going to be 3 right there. So we just leave it like that. But we do have to say my du. So du is equal to root 5 dx, or we like to write that as du over root 5 is equal to dx. So then manipulating that formula, what we get then is this is equal to, and I'll just pretend we're going like this to here. And so what you get is this setup. You force it to look like that integral. So what you have is 1 over, and then on the outside is your 5x squared. So if you write 5x squared here on the outside, it wasn't there originally, right? I mean, there wasn't a 5 here. So if you put a 5 here, then you have to put a 5 on the outside so that it's really just 1. So you go ahead and place a 5, and let me change the color, so make it a green or something. Okay, so here's your 5 that I placed in there. So now we're still equivalent to the original question. And then it's the square root of the 3 is still just 3. That doesn't change. And then plus 5x squared dx. Now I haven't done my du substitution yet. I'm about to do that. So this is the integral. And so now we want to write it in terms of the u. So 5x squared is u squared. and then it's the square root of, and then we can think of this as root 3 squared. So my a is root 3. I mean, you do have that a is root 3, but it really doesn't matter in terms of substitution. So then you have root 3, okay, then it's plus u squared, because that's what 5x squared is, du. But my du had this root 5 on the bottom, so that I'm going to have to take out front as well, and I'll end up with the 5 over root 5. So it's 5 over root 5. Okay, so now, oops, don't forget the 1 on top, right? Gotta have that thing. Okay, so now look at the form. You have your u squared, a squared, plus u squared, and then your du. So this is exactly the form that we need to apply the formula. And then here's your this is your integration constant. This 5 is just there to basically force it to look like that formula. So now that just hangs out there, and you apply the formula. So you don't integrate, you just go right to the formula. And then, so you get 5 over root 5. And then, so we're substituting into here. And so you get negative square root of 3, because that's a squared, plus x squared, all over 3 times root 5x plus c. And then we can simplify that a little bit. We have, oh, that's what I did. 5 over root 5 is root 5. This is just some algebraic manipulation, a little. It's arithmetic, I don't know what you want to call it. Square root of 3 plus 5x squared over 3x root 5. And so now, what I did is I took, I'm going to erase this. So I just rationalized that. And so by doing that, you end up with 5 root 5 over 5, which is root 5. So that's how I got from here to here, but that then allows me to then cancel that. I suppose all you could even, I mean, it's even simpler just to do this. Just take out the root 5, and then it's root, and then you get 5 over 5. So it just simplifies. Either way, it doesn't matter. Okay. So then you get, and then I did highlight that, real cool looking in the red here. So that's reduced to 1, and you have just minus the square root of 3 plus 5x squared over 3x plus c. So that's how you do the tables. You have to force it to look exactly like this before you can do anything. And you still have to possibly do a chain rule of du to figure out that integration constant. It shouldn't be anything except an integration constant, generally speaking. Okay. So now the nice thing is the integration itself you're not really doing, but you are doing the, you got to set it up to look nice, and that can be difficult. Okay, let's do another one. Next example. Let's see here. So next looks like this. You have the integral of e to the x over 1 minus e to the 2x raised to the 3 halves dx. So I'm guessing on this one we're going to look for my when you do your substitution, you need to get that e to the x gone. So this will be the case I just mentioned, see much, although we're going to see it right here. Watch what I mean. So, well, what you want to do is look for something that's a 3 halves. I mean, there's not a lot of them that are 3 halves, right? So we're going to look for something in 3 halves. This is a square, so we're going to use the idea that my u can be, well, actually, let me back up. We can use the idea that e to the 2x is really just e to the x quantity squared. And so this is a squared, and then 1 is squared. So the denominator form really is a squared minus u squared to the 2/3. So this is what you look for. And so you can use different tables. And so you'll be able to use any table. I mean, the really point is not the tables. It's just if you have the formula, how to do it, how to set it up. So, okay, so copy this down because I'm going to have to go to the formula table, and I'll show you what you do. Like, you kind of know the form, and then you want to look for that 3 halves thing. Let's just do this too. If I let my u be e to the x, then my du is e to the x dx. And so the e to the x dx right here, here's your e to the x dx. So that may be able to simplify right away with my du. Okay, so copy that down so you have a separate page to look at this. And then let's look at the tables. So I have posted these tables, and so here's all the tables. There's a geometric formulas, there's a trig, there's your basic integration, and then you get to more of the tables. And so you pretty much just go down until you look for something in there with the 3 halves. And you get down to here, and you can see, well, this is really the only one we have that has a 3 halves in it, right? And is it that form? Well, you have a 1 up here, and then a squared minus u squared. So yeah, if we do the right substitutions, I think we can force our equation or formula to look like that. So let's copy. So I'm just going to copy that over, and we'll see how to work with it. So let's bring that back and paste it in here. All right, so now we can manipulate the integral expression to simplify it. So let's see what we got. So this is equal to, and then we can rewrite this as the square root. And then this is e to the x over 1 minus e to the x squared, all raised to the 3 halves. And it's hard to do a fraction so small. dx. And so let's look at this form exactly. So my du is this, okay? Here's my a, which is 8. That's easy, right? You don't even have to write that down. A is 1. A squared is 1, so A is 1. And so if we apply that formula directly, we're going to get basically all of that. It is the exact form we want. So u is e to the x. A squared is 1, and then it's the square root of 1 minus u squared, which is e to the 2x. Plus c. So I could substitute in for u, but I didn't really have to do that because I can see it. I mean, this is my u here, and there's my du. And so if you did that, you'd be okay. But so my du is this, and then there's my u. And so I have this exact form. And so then you go to here and substitute for your u. Okay, let's do one more. I mean, you do want these, you just gotta practice these things. And then force it to look like that if you can. The formula that looks interesting, or close, I mean. 3x minus 5, quantity squared, dx. This one is a little different. Well, this one, I'm just going to kind of show you what you do after some thought, I suppose. So you'd be looking at your tables and you'd be like, well, if I rearrange this to negative 5 plus 3x squared, it might work a little better. And so let's look at tables that have something that's a sum of two things, and then a square here and a square up top. So let's go back to the tables. And so it's not a root this time. And then, oh, wait, look here. It's sort of like that. Right, it's in that form. And then you have this one. Oh, wait. Oops, I just pointed to it. I didn't mean to do that. What about this one? Why is it not this one? Well, because, and so write it down. If you go back and write that one down, this wasn't squared, so it's not that one. And then it can't be this one, this one, this one, this one. Let's see, what about this one? Well, no, because there's no squared there. No squared there. None. So this is the one. So this one, 53, has my form. I have the square and the u squared on top. All right, so I will copy that over just like I did on the other one, and we'll just apply it. Normally you wouldn't just copy it over, but this gives us a chance to talk about it. I'm going to paste it down here. Probably shrink that, put it up there so I don't use 2 pages here. And so let's do our, so take a moment here and see if you can figure it out. You want to let A be something, and what's your B, and then what's your U. See if you can make it look like that. This one's actually easier, I think, than above. So A is negative 5, B is 3, U is just X. That's it. Once you figure that, then you just plug it in. You can literally just go directly to the formula on this one. There's not even a u to do. I mean, your u is x, so du is dx. Substitute it directly into the formula and you get 1 over 27 times -5 plus 3x. Formula's messy, huh? Holy cow. 25 over 3x minus 5 plus 10x natural log of absolute value of 3x minus 5 quantity plus c. That's more the type you want to use and not have to manipulate like we did above. But that's how you apply it. So both cases, 1 and 2 here, you had to manipulate this a little bit to get in the right form for both of those. Sometimes you do, sometimes you don't. But again, you've already done this really a little bit with like trig, tan inverse, sine inverse. Should be practicing a lot of those. So you need to practice, and I have posted more examples of all of these in the files. Okay, so that's tables. One video on that. We'll do improper integrals next.